Alright, boys and girls, welcome back to the drive-thru for a special remix audio edition. This is chapter 12.4 on increments and differentials, and we're going to do some estimated error using calculus in this section. This is a little voiceover that I'm doing right now because the original video doesn't have any audio. So here we go, we're going to play it. Okay, so here's a definition of total differentials. Okay, and dz is how we represent the total differential. So if you have z, a function of x and y, then we're going to be able to represent the total differentials, and I'm just going to wait for myself to play it. 10 minutes max. Alright, so the total differential dz is the change in z with respect to x times dx plus the change in z with respect to y times dy. We could also write that as f sub x of x comma y times dx plus f sub y times of x comma y times dy. So you've got basically the partial derivative with respect to x times dx plus the partial derivative with respect to y times dy. Okay? So what we are identifying is dx and dy as little partial smidgens of change in x and change in y. So first, let's just practice the actual calculus behind this. So we've got our function z. Notice that it is just a function of x and y. That should be a plus there, I think. Also, we're going to write out the partial derivative with respect to x. So notice the derivative of 2x sine of y is just 2 sine of y with respect to x. Now we're going to write out the partial derivative with respect to y. All I'm showing you right there is that there are different notations for this that the book will use, so don't get hung up by the two different notations. They both just mean the partial derivative with respect to. It's very easy to make mistakes in trig when we're doing partial derivatives because you guys want to use your chain rules, when in essence, in the first one, sine of y is just a constant. There's no chain rule to use. So now that we have our partial derivatives, we can find our total differential, which is dz, by taking our partial derivative with respect to x and multiplying by dx. Bless you. And take our partial derivative with respect to y and multiplying by dy. At this point, you have no idea what the heck this is doing. We're just practicing the actual nuts and bolts behind the calculus, okay? But what you could kind of imagine is that, like, if we were to multiply both sides, like this by dx and this by dy, you would get d2z over dx dy, and if you kind of come back and watch this in a couple days, then you'll start to put together section 12.4 with section 12.5, where we're going next. That should be it for this one. I'm probably just checking my answers to make sure that I didn't make any mistakes by treating x and y as a constant. Okay, so what we're trying to be able to do here is predict our error, okay? Obviously, this can be very useful in engineering when you are forced to make your products under specific or specifications, which are called specs. Okay, so if you're going to make a bolt, your bolt is expected to be accurate to a certain specification. And that's so that you can predict the success of your product, and you're not always taking back your crappy little parts that you make and having to lose money doing so. So, here's an example. We know we're trying to estimate the volume of a box and estimate the air in a volume of a box. They give you the air in millimeters, but the measurements of the box are in centimeters. So I had to, King Henry drank many Diet Cokes Monday morning. You remember that one? Okay. I had to figure out how many millimeters were in a centimeter. So that's what I just figured out first. There is 1 millimeter, or 1 millimeter is equal to 0.01 centimeters. So, now I'm widmaploing. Notice that I kind of went with like what I'm used to from geometry as far as X, Y, and Z, but those are backwards compared to our right-handed system. 20 might be a better representative for X and 50 for Z, but it won't matter. You can call anything you want the length, you can call anything you want the width, and anything you want the height. A box has no orientation. So now what I'm doing is I'm writing the partial derivative with respect to X, the partial derivative with respect to Y, and the partial derivative with respect to Z. And so the total differential, the total change in volume, okay, will be the partial derivative with respect to X times delta X. And as delta X gets very small, then that will become dx. Right now, it's just delta X, and we have that. So eventually, we're going to be plugging in that 0.01 centimeters. That is our delta X. So it'll be plus xz dy, or delta y here, and plus xy delta z. So what we actually want to do is find the propagated air first. The propagated air is the amount of units that we are off by. Okay? So the propagated air is going to be in the same units as whatever units we calculated. So volume is going to be, in this case, cubic centimeters. So our propagated air will be in cubic centimeters. Relative air is going to be a percentage. That's a more useful value, okay? And you could expect that, you know, once you have a job someday, whatever that job is, that you're going to need to be successful to a certain expected rate. And the relative air is a better way to keep track of that success. So here you go. I just typed in, I'm just plugging in what my Y value, my X value, and my Z value are. You can imagine that if you called your X 20 and your Z 50, your numbers would look different, but when you think about the commutative aspect of this, it's not going to make your answer any different. You're basically adding the same three products no matter what you call which. Hopefully you can see that behind the... Oh, that's my toolbar. There you go. Okay. We could be off in the positive measurement, or we could make it too short, so I'm just plugging in those plus and minuses for my delta X right now. Notice, that's part of the given information, so all we got to do is include that in our answer. So we could be off by 20.5 cubic centimeters. That's the estimate, if you will. So, to find our relative air, we would need to calculate the actual volume of our box, which should be 100, so 1,500. And you put your air over your actual value. You can tell how much dumber I get by the end of the week because it's taking me that long to do 50 times 20 times 15. I probably used a calculator. Oh, and it's 15,000. Which one is it? 100. Oh no, 50 times 20 is 1,000. Turns out I'm better at the end of the week, but more confident at the beginning of the week. Well, that's good, because I felt like 20 over 1,500 was a lot of air, where 20 over 15,000, our relative error is 0.14%. Acceptable. Boom! Uh-oh. Where is it, Ratchet? This? Where? Oh, yeah. Boom!